Hello. Ooh, oh, that's the wrong scene. There we go. I was like, why is my desktop audio not here? It's because I'm not in the right place. Hey. Hey, everybody. How's it going? I would say that. That's just something you say, I guess. Nobody ever really means how, well, I guess maybe they do. Who knows? That's one of the most neurodivergent things I've ever said. Anyway, dynamics. We are getting into the meat. We're cutting to the chase. We are strengthening this beam, as it were. I have read a lot of things on this. I have many images that I would like to show because they are pretty cool, actually. But anyway, let me just check a couple things before we get into it. So, just for a little primer, it's like, why not? What did I have up here? This is what we were doing last time. This problem. We were given some r vector in terms of t, our parameter. I'm dying right now. That sounds it sounds bad. Don't die. 60-second ad? Oh my god. Twitch sucks, dude. I wish it would let me turn off all ads, but it doesn't let me turn off all ads. I could... Oh shit, I need to keep remembering. I should do a pre-roll ad before. I'm sorry. It's okay. We didn't start yet. I was just saying that this is the problem we were working on last time. We're given an r vector in terms... so a position vector in terms of x and y, related with this time variable t. And we have it's a little parametric, or this is also defined as path coordinates or intrinsic coordinates are two different names for it. I like intrinsic because I feel like path is a little bit, I want to say derivative. That'd be a funny joke to make, but I also forget derivative. Something that's based on another source. Not really the word that I need to use. It's not specific. I need sleep in 2 minutes. Then you should sleep in 2 minutes. The VOD will be here for you. There will be some early morning Damie at some point. Is that a lie? I don't know. Maybe. But I'm live. Yeah, I am live, but I'm live a fair amount. Well, not on UK times. Because I have classes in the morning. I have classes from 7 to 9. And then I have class at 12. So it's like, when would I go live? I have to like leave for my class at like 11:30. What did I think of the... Oh, the Minecraft mod screenshots. I thought they looked cool. They looked like this, kind of, honestly. They looked like math, and I like that. I had a list of things that I was going to do. Let me look at the things that I was going to do on stream that I took notes about. Let's see. This is the level up music. We're leveling up today. Okay, it says, check out Calc 3 work for best way to graph parametric functions. That's fair. This is my Calc 3 notebook that I have right here, I think. Let's see. I couldn't remember if I had, I was trying to graph this function, right? And we kind of just plugged in t, which you can always do. But I just wanted to make sure. Tangents to polar curves. That is not what this is, but we could get there. Because I have some points to make about this, but I'd like to see if we can find infinite zero. Okay, that's gonna be, I think we did it after. Maybe we did it before. Here, my page turning. My brain is not ready for this. It's okay. It's actually not that hard. I just need to look up one thing. And then I actually do want to talk a little bit about this because rarely do I have a class. Least viewed math streamer? Hey, don't be mean. I'm the most viewed in my heart. I'm the most viewed Catboy math streamer. To be fair, I'm not really doing math, but they don't really have a dynamics category I can stream in. Okay, so let me... Is this even plugged in? Hello? Hello? Not gonna lie, I didn't know other people stream math. Yeah, people do. I'm the best. I'm kidding. Most watched math VTuber. There are other VTubers who have done math, so I don't even think that's true. So I do want to talk just a little bit about motion, I guess, of particles. So that's what we're doing in dynamics right now. So if I draw a coordinate system, we know this guy, the Cartesian coordinate system. We have an x and a y. And we have a particle moving around in some way. Right, it can be whatever way. There's potentially there's not, depending on the function. But depending on the function, if you can define this as an f of x in the Cartesian coordinate system. I feel like I know that thing on your desk. The thing on my desk? Okay, so we have this function in the Cartesian coordinate system. I'm on sleep meds. Oh. And the way that we define this is by saying for every x that we have some y, right? So we put in an x and we get out a y. Now this is not entirely true because like there's two y's. There's three y's for this x, but we're gonna pretend that let's just pretend that we can do this function. Makes me EP but not EP enough to miss stream. Aw. That's so nice. Okay, so we can define this function in terms of for every x we have y. If we have two other coordinate systems to choose from. We have polar coordinates, so this is Cartesian. We all know that. We have polar coordinates, which defines it based off of an angle and a radius. So we draw a line from our origin, wherever that origin is, to... Oh, you're heading out? Bye. So we draw a line from our origin to our point, and this is going to be our radius, and that has a length, which is how far out the particle is. And we have a theta, which is going to be our angle up from... I mean, again, we can choose any reference point. It could be like this angle, but generally we tend to choose this angle right here as theta. So we have these two ways of doing it. We also have another way of doing it, which is we can define... So in polar we have an r and a theta. In this we have an x and a y. A function of x, y, right? We have another type, which is like parametric, essentially. Which is funny that people don't really refer to it this way, but it's parametric or path, or some people call it intrinsic. Because in this sense, we have a function of x with one variable and a function of y with that same variable. So it's sort of like we've taken this and we've ballooned it out, right, to say there's a direction that this particle is moving, and it's not just that as we go along in x it's going to change, it's as we go along in time it's going to change, right? And we sort of define that the same way because we can have an r vector who is defined by x sub t and y of t. So we have these three different coordinate systems, and this r is the same thing. It goes from the origin to the point. Now, in polar coordinates, we can choose a different origin. In parametric, we can choose a different origin, right? So it could be, we could say that our origin is over here. But the different thing is that when we're talking about our unit vectors for talking about acceleration and velocity, we're going to have different unit vectors for each of these three coordinate systems. So for f of x, put it in red, we have I hat and j hat, right? Those are always completely the same. So if this particle is moving over here, we still have, right, I hat. I'm not going to label them over here, but we still have I hat and j hat, which are pointed like that, right? Stretch? Oh, I got you. I'm doing a little stretch. Cracking my knuckles, sorry. Oh, I really need to stretch. I need to like stretch like actual better stretches, not just like stretching stretches. Stretch of dance practice tonight, so I'm gonna be stretching a lot. Okay, so we have these coordinates, which are great. We hopefully are pretty familiar with those. But we also have some polar unit vectors, right? Because it's a different coordinate system, we have different unit vectors. So one of them is going to be this one, which is r hat, and we define that to be a unit vector's length 1, and that's going to be along our r. So over here, right, we have to draw the r, and that's going to point outward like that. And the unit vector always points outward, but obviously we can have a negative radius to point inward too, right? And if it was negative and like all the way over here, that's how you can have functions where like your r goes backwards, but that's just classic math polar stuff. We also have unit vectors for our parametric equations, which that probably made that very hard to read, but these are going to be a little bit different. So we define one of our unit vectors as a tangent to the curve. Oh, I didn't draw the theta. What am I doing? we have theta too. Shit, wait, go back. Okay, so theta is going to be perpendicular to r. So it's not always, you see how it's not always pointed along the curve, but it's just 90 degrees to r like, I think of it sort of as to the left, quote unquote, of r. It's like counterclockwise to r. You can also think about it as if you do r cross theta, you're going to get a positive number because it's a right-handed coordinate system. That's how we define that. So in this case, because it's kind of close to a circle, we have our theta is kind of normal to or tangent to this curve here, which, I don't know, I can just call this A. But it's not always necessarily normal. It's just 90 degrees from this. Sort of how like I and J are 90 degrees. It's a pretty common theme to have stuff be 90 degrees. Except for when we get to path. So the funny thing about path is we're going to define two unit vectors, and I'm going to draw them over here first, because our first unit vector is going to be our tangent vector. So when we take the derivative of a parametric curve, we do r prime, we get x prime of t and y prime of t. And we know that when we're trying to take the instantaneous slope, and that's going to be the normal to this line. So in this case, this is called e of t, e sub t, because it's the tangent. That is really hard to see. Okay, I'm going to make this a little bit orangier. Kind of see it a little bit better. Better to see e sub t. Yeah, it's a little bit better. We have e sub t, and then we have the same thing over here, but it kind of isn't. It's kind of the same. You can see how in some cases, right, e sub t, which is normal to the curve, and theta can overlap if it's a circle, which is kind of where we're headed. We've got that. And then we also have this second unit vector, and third, if we were in 3D, because when you have a coordinate system, you have as many unit vectors as you have dimensions, or if you have, variables, essentially. So our second one that we're going to do is we're going to define a what's called the normal vector, which is a little funny because it's not normal to the path, it's normal to ET. Sometimes. Not always normal to ET, which is also confusing. But what it's actually going to do is it's going to point towards the center of the curve that we're curving around. So in this case, it's going to kind of point almost like in the same direction as R, but negative. Because that's where the center of the circle is. And as we go over here, this circle is getting bigger and bigger and bigger, so it's going to get longer and longer and longer as we go along that center of curvature. So we can see in this funny little picture, this is why the title of my stream today is Unraveling the Tangle, because looking at this, it's like there's so many different things that you could be seeing here, right? Like, I mean, understanding the relationships between these two when they line, these three, when they line up, when to use them, how do we apply them generally versus in specific cases. Those are all sort of things that you have to be, you know, comfortable with, and some stuff that I'm going to try and wrap my head around today. So that's like my intro to these different coordinate systems, just so you guys can have kind of like a basic. I have some great images. Wait a second. I actually have some wonderful, wonderful images of these different things, which I think were awesome for me to see. Okay, so this one is for polar. These are all moving, because I was very specific. I was like, I want to make sure I find things that are moving, because, wait, let's go to full screen. Let me just make sure I have this on the right thing. There we go. So this is the first one. This is a, and I may or may not, if I remember, if I can link all these GIFs in the description of the VOD of this. But so we see, first off, we know this is polar because we've set like an origin and this radius is pointing outward. You'll notice that this is an ellipse, right? So it's gonna have two sort of origins that we normally use to define an ellipse. That's just sort of how an ellipse is defined. So they chose one of the origins there. And we can see that our ER always points outward, and our E theta is gonna sort of be normal to the curve right there. And as we come around to the other side, right there, but that our ER, you know, it's not always relative. We can see though that our acceleration is still pointing towards, well, it's an ellipse, so I'm not going to pretend like I know exactly how the acceleration around ellipse points, but it looks like it's pointing towards this origin, and then it comes around to point towards, is that an E or an epsilon? So, great question. One of them is epsilon. I'm not sure why, because they're both just unit vectors. So I think you can define them as you will. I think it might be an epsilon because E theta is tends to be a derivative of ER. So if your R is your sort of position, the way that you derive the other one is from it. So that might be why it's an epsilon, but it's definitely epsilon theta. So we got that one. That's for polar. This one is great. This one is for path coordinates, and this one was the one where I was like, okay, this actually rules. So we can see that as we go into these tighter turns, and I'm pretty sure the red is an acceleration, not just a, not just the vector of the direction of it, but we can see that as we go around these different curves, it's switching. Okay, metal pipe. wouldn't be a good dynamic stream if we didn't drop some metal pipes. I mean, that's like classic dynamics, right? I really like this part where it goes like all the way over here. That's my favorite part of it. The other cool thing is, like, if we have a line, if it's just traveling on a line with zero curvature, that's actually an infinite radius of curvature, right? Because the circle is like so big that it's flat. You've like zoomed into like this infinitesimally small piece of the circle. It's just flat. So when curvature is zero, the radius becomes like infinitely large. But yeah, this is acceleration. So we see our velocity vectors pointing always normal. So it's just kind of pointing like if you were driving the car, essentially, like where you would be kind of driving the car. That one's pretty good. Where's another one? This one is actually really cool. This isn't really like as much of a math one, but I think this one illustrates, it's a Tumblr GIF actually. But you can see sort of the radius of curvature getting bigger as we go to the really big parts, and then as we get into these tighter turns, it gets smaller to kind of match that, which I think is pretty cool. Unnecessary disorder. I don't know if this person stole this GIF. It might not have been the author of the GIF. But we're not here for academic citations. We're here for a cat boy on the internet. Molding over dynamics. Very elegant though. Yeah, it's really beautiful. There's some other ones. This one is also pretty great. I was really looking for stuff. It turns out searching for curvature is a little bit better than searching for like curvilinear motion. So yeah, we can see the tangent and the normal vector. The normal vector is always pointing into the curve, but our acceleration can point away, depending on if we're like slowing down or speeding up. And you know, there are lots of different components to acceleration when you do polar coordinates, although this is path. I think the other important thing to sort of note, at least from me, who's coming to it from a math perspective, because a lot of this, you know, can be applied to dynamics, but also you would be learning it sort of in a math way first. Like I learned this in my vector, very cool graph. I know, right? Isn't it awesome? I learned this in my vector interesting function. Yeah, it's super cool. After my vector, sorry, intro to vector stuff, because we talked about like curvature and curl, and that was all talking about like different derivatives and kind of getting as an intro to multivariable. There are certain constraints that these problems are going to have, and certain cases that we're going to use a lot more, just because of the way that we model things in the physical world. So a lot of the math can still apply. Like for example, you know, if we find a velocity, like an angular velocity or something, with one coordinate system, we can still convert things, we can still like project vectors onto another. So it's always good to just like keep those math tools like on you, and don't just like, you know, forget everything and try to go back to caveman type stuff if there's still elegant math solutions you can do. We keep that thing on exactly. Yeah, that's one of the reasons why I was thinking about trying to do a little bit more lecture type, getting back into more lecture type stuff with the sort of study with me that I do, because I think that I'm quickly learning that a lot of my professors don't keep that math thing on them, and I am getting a little bit bored with how much it doesn't show up. Because like, we were doing this one thing, and my professor was like, okay, we're gonna like try and figure out how much of this vector is going in this direction. I was like, oh, projection. He was like, we gotta figure this out with geometry. And I was like, no, how about we don't go through all that? So, okay, I hope that was like interesting or useful, or, you know, kind of helps contextualize some of the stuff that I'm gonna be doing. But I'm gonna delete the other time I started this problem, because I find that just deleting things and just chucking them out there, getting rid of them, and then just restarting them is a lot more useful a lot of the time, which, oops, I gotta go over here. But we are gonna be working on, not this one, not this one, not this one, not that one, not that one, this one. So, we're just gonna be doing some derivatives. I wanna update my equation sheet first. So I gotta get my little, we got a lot of equations that are sort of poorly, like for example, we talked about the Coriolis acceleration. Is that useful? Not sure if knowing the name of that particular acceleration is the most useful thing, but sure. Now I know that. That's the thing that's in my brain now. Oh wait, she moved the date for it. Oh. Well, we're gonna do it anyway. Woo! She made it due later because we did not learn all the stuff, but it's okay. We boldly go. We boldly go where no Capway has gone before. I'm also gonna get rid of the answer on this one because I don't want to see all that jazz. This is just what I was doing before. Alright, okay, let's go for it. Before we do this one though, let's go to our equation sheet and update that a little bit, because right now our equation sheet's looking a little lacking. It's these three equations, which is great, but also, there's a little bit more than this. So let's see. We got some, let's do some, okay, first off, let's put kinematics on here, because I'm forgetful. It's not like it's been a year since I've taken physics. Kinematics, so we got V minus VO equals AT. And just chucking these on here in no particular order. Maybe I should move this over here. There you go. These are all sort of our basic kinematics type stuff. You know, we use these for our constraints. These are like very, I'm gonna do delta S equals VOT plus 1/2, our good old buddy 1/2 AT squared. Everybody 1/2 AT squared, everybody loves that one, everybody loves that guy. Envy is so bad? What's up, you're not in a physics class right now? I really like physics. This, like, dynamics feels a lot more like physics than statics in, like, a good way to me. Like, it feels like we get to do more math stuff. Although I liked the modeling of statics more. But you get to do that in dynamics too. Okay, now we have the chonky boys. Where's my chonkers? Okay, so for our path, sorry for mouth noises. Intrinsic. It's a beautiful word. That's why I use intrinsic. I think it's like, I just smile when I say intrinsic coordinates. Isn't that like a gorgeous word? Good mouthfeel. So much better than path. Also, like, path makes me think of path integral, or like a line integral, and it is absolutely 100% not exclusive to this coordinate system that you can do a path integral with it. So, you know. Okay, so we got A equals the let's do velocity first. Velocity is going to be our velocity, our tangential velocity, times our, probably shouldn't do a dot, probably should just write it. There are some dot products. Basically just our physical value of our velocity, so our speed, our tangential speed, and then our in our tangent direction, right? Because this is a unit vector and this is just going to be a number. So it's technically not velocity speed, but you know, they refer to it as speed because it's going to be a function and we take a derivative and yada yada yada. Okay, so then when we take the derivative of this, we do a bunch of math and we get that that if we take our derivative of v, we multiply that by the tangential velocity. If we have, okay, so let me do a little clarification here because I'm going to write something and you're going to go, what the hell, Damie? Yeah. Okay. I know what you think. What's rho? Well, in my class, and so, okay, I'll take it from two sides. I'll take it from the good side first. Sometimes when we have path coordinates, or sometimes when we want to use path coordinates or intrinsic coordinates, we might not know the function, right? So that's sort of like this example that I was doing, not this one, this example here, where like we don't know what this function is. But one thing we can know is like its instantaneous velocity. We can know about its instantaneous position, vector, length. These are all things that we don't need to know without knowing the function. Or that we can know without knowing the function, right? And so, you know, there are a lot of cases, because just of the way that modeling works, that we want to sort of center things on that instantaneous point in time. So what essentially this equation is saying, okay, for a given radius of curvature, which is rho, and like a given velocity, we can use this. And this is going to be, right, an acceleration value, a tangential acceleration value. So this is really just saying like at a snapshot in time, because we don't know this function. Maybe it's like a person driving a car, right? Like that, you might not know that function. Might not be easy to model. Might be like a 6th order like equation or something. Although you can always approximate closer and closer and closer with enough points, but I digress. You know, if we just simplify and we just use this to say like we can figure out, you know, maybe an total acceleration, or maybe we have something, we know some things about like the total acceleration and we want to find its tangential velocity, its tangential speed, what have you. We can figure this stuff out. The bad way of thinking about this is that my class doesn't think we're smart enough to do integrals consistently. And so they just only limit us to doing intrinsic coordinates with at an instantaneous point in time, which I think is maybe more true than the other part of it. But it is a fair thing to say, like, in the world. This is just sort of a specialized case instead of the integral version, because if we have the integral version, you can say there's a version of this that you can say what happens if R is a function, right? Like if you have a position vector, you can still take the derivative and do stuff with that, but it's just a little bit more complicated. Okay, so we've got those. Those are for intrinsic coordinates, and then we have our polar coordinates equations, which are also interesting. These are just our various coordinate equations, so I'll keep them in the same sort of area. We're also going to have a velocity, which is a little funny, silly. So velocity is going to be, I'll use dots. I'm personally a prime fan, so like v prime to denote a derivative, because that's the notation that I learned in math, and I think it's kind of elegant, and if you're typing it, it's pretty easy to type. But I'll do a dot because for some reason it's a time derivative specifically, the dot. Like, so this would be dv dt instead of just like, you know, we're taking a prime, it's some derivative, we don't know necessarily what that is. So in this case, we have the derivative of our function, which, remember, in polar coordinates, that's our radius outward. It's not defined as, it would be defined as a single sort of variable thing, right? So if we had, like, you know, 10 theta, right? We're not going to have, like, 10 theta comma 20 theta or something, whereas this is for polar. Whereas for intrinsic, we would have, you know, cosine t, sine t or something, right? Where we don't have this, we just have this. So that's just something to keep in mind for our quote-unquote, like, radius, right? Even though in this case, we don't even have a derivative, so we don't have to worry about that. It's just going to be a number in that case. So it's going to be the change in R times our unit vector in R, and then we're going to have, oh my gosh, it's silly. How's it going? We're going to have our R theta times our theta direction, which kind of makes sense. R is going to affect how much theta changes because of arc length stuff. And then for our acceleration, it looks a little beastie, but that's okay, because we love him anyway. This part is fine. We take a second derivative of this one, and it's product rule, so we do... oh wait, I lied. This is not exactly the way that we write it. We write it usually like this. Now, I'm not going to attempt to derive this or explain this derivation because it's not great the way that I learned it, and I would preferably have a different way. It also took an immense amount of time to explain during lecture, and, you know, it's not necessarily worth it. Essentially, we just take the derivative, but, like, we can combine some terms and switch some terms out, and so, like, we can see that this is going to be the derivative that goes in here, right? And we get we're going to get like an R. We're going to get a determinant of this, which is going to give us this portion of this. You know, going well. I'm just making a map right now. How's dynamics going? It's actually going pretty well. We got our equation sheet set up. We did our, like, little contextualization thing with this funny boy. We looked at some fun GIFs, and now I'm gonna just jump in. We're gonna tackle the problem that we did last time. First time chat, not like this. You don't like it? You don't, what's wrong? You don't like it? I kind of like how it ended up as clown colors, I didn't really mean to make it clown colors, but it's crazy how the more you go into math, the less numbers there are and more letters, frankly upsetting. It's crazy how when you go into math and you study it more, the more you're like, thank God there's more letters and less numbers, because the most mistakes anyone ever makes in math is when they start putting numbers into things. The amount of mistakes you make on letters is very low compared to the amount of mistakes you make on numbers. At least for me, and I think for most people as well. It's okay. It's just like a different language. Because like really what we're saying when we say like this, right? You're like, what is that? This is just a shortening of saying the change in the speed of the radius length changing. The change in speed of the radius length. Dynamics like dynamic systems, right? I think maybe that is more complicated. Like, I don't know if you're so like yes and no. Like, for example, one of the things that like we study is, you know, this is just a very, okay, that looks a little odd. Let's maybe make that, it's a linkage. Okay, I swear it's a linkage. It's a linkage. I can't draw it very well. We have like, you know, if you have like a slot and then like a link in that slot and this slot is turning, then like how fast is this thing turning? So you can do it for stuff like that. It's just like a lot of these equations. I've only been taking this class for like 2 weeks, so we're not there yet, but yes, it is dynamics. Like there are some systems. It's not like, I think what comes to my mind when I think systems is like, here is an entire car and let's model like every part of it, and that's what a dynamic system is. But it is dynamic systems, not like kinematics of like, oh, I shoot something out of a cannon. Although we do some of that, drop things out of planes, what have you. Okay, so let's define our little funny position vector. Imagine if we were using any of these equations in a real-life setting, that there would have to be some form of error component in them. Well, I have great news for you that's also awful news. I had to take an entire course on that, and the VODs are not yet up on my YouTube, but they are up on YouTube. Essentially, the only error that you can really have, there's like a couple different kinds of error, but you can have error from measurements, or you can have error from like models. Right? So if you have error from measurements, you basically can do this sort of propagation thing with the error, where you can take some derivatives and say like, okay, if this is changing this much, then how much does that affect the error overall? But if you have error from your models, you have to kind of, there are different ways that you can like kind of counteract that error as a designer by using like safety factors or but sometimes like with models, it's like we don't know what the real model is, so we can't necessarily know exactly how far we are away from it, right? So that's why we do something like a safety factor. Like, let's say, oh, we have a load limit and we calculated it to be like 100 pounds or something. Well, we're gonna really build it for like 150 pounds and say that the limit is 100 pounds so that we're not killing people or whatever. Noticing a lack of plot-driven character doodles. Who am I supposed to draw? This guy? I mean, I can draw 10t minus 5 sine t r vector. See, the thing is, like, I do have. All right, you know the true function, but you're doing your damnedest to estimate it. Exactly. You don't know. Yes. It's actually a very fascinating sort of space to be in, because the concepts of the course that I took are not actually that hard. Like, I could teach a lot of the stuff that I learned about that course, like, in probably like 1-2 hour lecture. I think a lot of people will be like, oh, that's pretty cool. That's pretty useful. So I might do that at some point. Okay, I'm going to draw this function as a guy, because why not? Okay, let me think. He's like an oscillating guy. I think he's going to be a bird. I'm going to make him a bird. We're gonna be working with this guy, so like I might as well draw him. He's gonna be a bird that like looks like this. I don't know what that is. That's his foot. Okay, he's got 2 feet. I don't know where his eyes are. His eyes are there. Oh, this is a little bit of a scary guy. No, you're totally fine. It just so happens that, like, because normally I'm more silly, but like no, I like drawing silly guys. It's always important to know the guys that you're drawing. That's our man, Mr. R Vector. It just so happens that I like was struck by a need to lecture because I was like, dude, my brain, I can feel myself like just like crumbling into dust if I don't lecture. Okay, we have to find the magnitudes of the. I'm gonna sketch the path last. Crazy, you're leaking the newest Animal Crossing character design. This guy. Turn this into my dynamics professor. Like, what the hell is this guy? It's like, oh, you know. Oh, you know. This is the most important part of my process. You hire me as an engineer, you are gonna get like a weird little guy like on half of the drawings I do.
Sexy await will return soon.
Sexy A-Wait will return. Oh, I started a drawing of Sexy. Well, Sexy A-Wait's not here right now. If Sexy... Wait, maybe Sexy A-Wait is in one of these problems. Let's see. I don't know if any of these are weight problems. Let's see. Peripheral speed of a saw blade. That's kind of sexy. Point A, not a weight A. Oh, we got a sliding pin. Intelligent young bird gentleman. Exactly. I miss her. It's okay. You gotta... There's so many faces you meet in math, you know? You wouldn't get to know R Vector if we didn't have... If Sexy A was just here all the time, you wouldn't get to meet this dashing young gentleman. I want to give him, like, a feather. Like, just right off of his head, like, a singular feather. I think that would be really good. Yeah. Okay. Now that we've got the most important from that away. Then find velocity. Wait, why did I draw it like this? Don't look at me, that's a vector. Important we know what is a vector and a unit vector. Okay, let's check our equation sheet real quick. Okay, so it's vt et. So we can take the derivative of these to get that. I'm pretty sure. I'm pretty sure? Or maybe we can't. I don't know, I feel like you can. Pretty sure you can. Okay, so the derivative is 10 minus 5 cosine t, and we got plus sine t. I like to imagine that when you take a derivative, they just get like kind of squished, like that. He's having a great time. You can't even see him though. He looks like a wee wee. You know like the peepees, these guys. This is my artistic skill. You gotta patent the VTutor thing, it goes so hard. Patent it? I gotta actually change my Twitch name. I'll do it. OMG, the little guy. Okay, so we got a V. We also need an A. I'm gonna just keep taking derivatives, because I feel like we can do that. But we want to know the magnitude, so we would have to take, because when we want to maximize something, we take the second derivative and we set that to 0 so that we can find where it's flat, like at the curves. You know, all that Calc 1 stuff. So if we take this derivative again, this is going to go away. The cosine, this will be 5 sine t, and cosine t. Which is kind of nice. So we set these to 0, and we find when v is, what are we finding? Like the local minima and maxima. So sine is 0 when we're at 2 pi or pi? Is it pi? It's pi. 8 pi. So t equals k pi, and then cosine t is 0 when we have t equals the opposite. We have 2 pi over 2 plus k pi. I remember math. Ooh. That's why we gotta practice. Okay, so at these points we'll have some sort of minima or maxima. So if we plug these both in, we can see which one is gonna be minimum and which one is gonna be maximum. These are our what are they called? Like turning points or something? I don't know. Turning points. I think they're called like big numbers. I don't know, they're not called that. They're called, what are they called? Something. Special dudes. That's good enough for me. I know what they are. I don't need to know their name. I know their vibe. Okay, so if we have t equals k pi, that's gonna be v equals 10 minus, okay, so for k pi, we just said sine equals 0, so that would be 10 minus 5. And for sine, that would be 0, so that would give us 5, 0. And then for t equals pi over 2 plus k pi, that's going to give us our 10, and then sine is going to be 1. Yes. So 1. You know who I really miss? Slinch. I hate Slinch. Wait, no, actually, I don't hate Slinch. Slinch is not gonna come back for a while, unfortunately, because we are not gonna see slugs for a while. I would also be very surprised if we saw slugs. I don't tend to see, I mean, a lot of slugs is the thing. Which, you know, you'd think would happen more, but like, oh shit, wait, I forgot. I can have a minimum. There's a negative I can have. No. I know, it's a little sad. My son with every illness. Yeah, Slinches, I mean, are a very specialized unit. I don't use them ever. I've only seen them in like, I've only seen them once. I think there's one stream where I was like, what is this? For data analysis. Maybe the first one I did. And then he never came back. Well, my other son with every illness is Skin Boy, and Skin Boy I actually love, unfortunately, so... Not unfortunately, I love Skin Boy. Okay, so when is pi is gonna be, or cosine is gonna be negative when it's over on the left, so that's gonna be, so the max we can have is actually, I'm gonna do this, so this is like pi plus 2k pi. Data analysis was one of my favorite courses from undergrad. I'm pretty sure that, like, it's a different course than mine. I called it it was engineering measurements and data analysis. I don't know if that's the same thing or not, but, yeah, unfortunately it's unfortunate that Slinches are so uncommon because I love how you drew him. It's okay, I draw a lot of little fucked up guys, as you can see. There will be more fucked up guys in the future. Okay, if I'm trying to minimize... Am I trying to minimize this? Well, let's see. This one is probably going to be our minimum, for sure, Z's. So we can get a negative number, but that doesn't really matter. It's only going to be 1 or -1. So it's going to be that no matter what. So that would mean our maximum velocity is, so Vmax equals 15, and Vmin equals 10 squared plus 1 squared. 100 plus 1 equals, I don't know what that is off the top of my head. Uh-oh, people are texting me. What is happening? Okay, it's not an issue. I see texts in my Lion Dance group chat, and I go, oh no, this is gonna be so bad. I put the square root on the outside. I wish I could, like, show you guys my calculator because it's not good. Let me see if that's right. I feel like that's wrong. I feel like 10.04 is not correct. Let's see. Vmin. Okay, 5 feet per second. How would we get 5 feet per second? What? Oh, when it equals 5? Oh, I guess it would when it equals 5. Because we can say 10 minus, so if cosine is positive. Okay, this one's kind of a little silly funny. If we have... So they're both happening when... it's kind of a little silly funny is the issue. Okay, this is gonna be 5, 0. Like, this one's not gonna be minimized, but that's fine. So it's either if we have pi plus 2k pi, or 2k pi essentially. And you know, my best friend, the unit circle. This is cosine. Cosine is just the x, and the sine is just the y. So positive for cosine when he's over this way, and then negative over this way. I love my friend, the unit circle. I wouldn't have it any other way. Vmin is not 10.04. Vmin is 5. Meters per second, feet per second. What are we doing? Feet per second, because we're American. It's fucked up that America uses feet. Uses the imperial system. Can we get a not like this in chat for the imperial system? I hate the imperial system. But the imperial system is Slinch, so if you like Slinch, then Imperial's here to stay. Sippy. Okay. The corresponding times, positions, and directions of velocities. Well, we do know the times, because we did find them. So if we're going from 0 to 2 pi, then... so the time for this one is actually going to be where we start, so time equals 0 seconds. And the time for this one is going to be pi. So I think it's just going to be... Okay, that's a little funny. Well, fine. It'll be 2k pi. Seconds is how she wants us to write it. Plus pi plus 2. Never tabbed in so fast. Never tabbed back in so fast. Slinch mentioned. Slinch is such a funny... I kind of also like Slugette. It reminds me of like a secret Mario character. Like, you know when we had like Bowsette? I feel like Slugette would be one of those characters. Just like a slug that got turned into Toadette somehow. Just living their best life. With like the little hair things. Yeah, that's accurate. I don't know how to draw a slug. That's kind of close. They kind of look like an egg. Slugs are eggs. Don't worry about it. Okay, positions. That's pretty easy. We just take the time and we just put it in the position. So for that one, oh, do they want us to do it? Doing it parametrically would kind of suck, wouldn't it? Oh, they want us to do it parametrically. Fine. So 10 times, so x max, I guess, equals 10 times pi plus 2k pi, which isn't going to be great for us. Minus 5 sine. My face when physics. That's such a cute face. That is also me, like just in classes. It's like me looking at my professor's proofs and being like, mildly distressed. Me and my professor that says that polar coordinates means that the radius is always changing and that path coordinates means the radius isn't changing at all, and I go, excuse me. The amount of times that I've tried just to not ask questions in my lectures has just gone so much up. I'm like, oh, I should probably ask a question about that. Maybe I shouldn't about that one. Okay, so for this one, why am I doing it all the way over here? Why am I so scared about our friend R Vector over there? I think we'll put all these guys over here so they can frolic. Okay. Okay, so we got X max. So we know that the sign for this, if it's pi plus 2k pi, what about our unit circle? we're over here, pi. Basically, every time it hits pi, that's 0, which is great for us. This is going to be 10 pi plus 20k pi. That's good enough. I'm fine with that. I didn't put k there, but 20 pi k is same thing. And then for x min, we have 10 minus cosine of the pi plus, or well, 2 pi. And that means that it's going to be all the way over here, so it's always going to be 1. Means it's going to be 9? Wait, that's, oh yeah, because this function actually goes like this. I mean, that's a really bad drawing, but it's like a, it's not like a sine, it's kind of really flat at the bottom here. So that would make sense, I guess, in the position-wise, because it'll always come back to sort of 9. Whereas this one would, well, actually, okay, that's not, it's not right. Wait, what did I do wrong? That seems weird. Let's see. 2n plus 1, that's fine. That one's 0, but wait, how do we get a thing out of that? That wouldn't give us a thing, that would give us a number. Because every time it's, well, okay, maybe they used a different time. It was 2n pi. No, same thing we did. If we put it into x min, oh, I plugged it into y, chat. I plugged it into y. I gotta plug it into x. Silly me. Silly me. Okay, here we go. 5 sine of 2 pi k. Also 0. There you go. Equals 20k pi. Pi k. Second difference. Okay. Put these over here. We're cooking. Plus 20 pi k. X min equals 20. Nice. Okay, now I think we only have one last little thing to do. Direction, right? Which is not my favorite friend of the bunch, but that's okay. The direction of the velocity. Okay, so to do that, we need to do a little angle. Bro. Oh wait, we don't actually need to do that much because we already found what the velocities are. So, oh wait, we don't even, wait a second. We're getting trolled here. 15, 0. The velocity is pointing this way. The angle's 0 for both times. Theta max equals theta min equals 0. They're trolling us. They're trolling us. What are they doing? I also really like how the sequence implies that, like, this is the velocity, and, like, you just turn it into a pee-pee when you... Okay, I shouldn't say that. Don't clip that. You turn into, the item label, plushy pee-pee when you go to take the second derivative, which happens to me in the morning. Only in the morning, though. My daily plushification. Okay, now that's also a little odd, isn't it? Anyway, we gotta sketch this bad boy. We've sketched him in the physical sense of what he is, a bird, but we need to sketch him in the numerical sense of what he is, which is a function. So we're gonna go from t, so 0 to 2 pi. Lovely little interval there. So we'll just say 0. We'll go old school with it. I don't really need to do that much more. We do know that at 0 it's gonna be 5, 0. We'll do pi over 2. Do pi. Get this song. 3 pi over 2. And then 2 pi is going to be the same, so we don't even need to do that one. Well, I guess I'll leave it in there. 5, 0. Swag. Okay, we also did pi, which is up here. That's 15, 0. Well, zeros in here, huh? That's for y. Is that accurate? Nah, we'll figure it out. Well, I feel like that's wrong, actually. Don't quote me on that. The pi, yeah, we would have sine equals 0, huh? Oh, but we're doing position. It's 10 minus. It's not gonna be that. It's also not gonna be this. It's also not gonna be this. Oopsies. Okay. So for 0, we have negative 5. I'm gonna draw the unit circle over here. So our sine is gonna be 0, so that first one is just gonna be 0 straight up. Second one is minus 10 minus cosine t, so that'll be 9. I believe. For pi over 2, that's up here. We've got 0 cosine again. Wait, what did I say? No, we have 0 cosine, so that'll be 10. We've got so we 10 times t, so 5 pi minus. Getting a little cramped in there, huh? 5 pi minus 5. So 5 pi minus 1. You and I have less than 1 pi. Okay, cool. For pi, now we're over here. So we've got a negative cosine, so that's gonna be 15. 11. 15, 11. Definitely. This one's gonna be 10, I think. Yes. Wait, yes. I'm learning. I'm learning. I can't really do that with this one, unfortunately. Or can I? Is the 3 pi over 2, that's gonna be here. That means sine is gonna be a... Why do you hear a Minecraft amp? Uh-oh. Does it sound like a Geiger counter? We might have a visit from our little friend. Or did I just make a mic? I might have just accidentally made a Minecraft noise. It might, if it sounds like the basalt biome, then we might be having a visit from my mic friend, unfortunately. Demon Core in Damie stream. Well, it didn't go red, so we're winning. 0 days without mic incident, unfortunately. We've made it pretty far, gang. We made it farther this time. Damn it. That's just 10t, so cosine is... Oh no, sine is 0. Yeah, so it's 10t. 10t, 10 times pi, 10 pi. I don't know what any of these values are. What the hell am I gonna do with 10 pi? And then sine is gonna be negative, so it's gonna be plus 1, I guess. So, no, not 5 pi. It's gonna be like 30 pi, 15 pi. Plus 5 pi, 5. Sure. Those are numbers you can read, right, chat? Right, chat? Okay, we can do some of these. So we know lovely y, always on my side. We got 10, we got 11, we got 9. Beautiful. Stunning. Now the problem child over here, 5 times pi minus 1. I don't know what that is. 10, 11-ish? I think it goes up to 60. 30, 40, 50, 60. We got 0. Is at 9. I'm building a peer-to-peer server and client. Can you explain the process? It's like in dreams when you have like a class. It's like, oh, you're taking a test for this now and you've never gone to the class before. No, I can't. I do not know anything about that. I have never built a server before. I have 2 CC. Okay, let me. I read that as CCP. You already can tell I'm not. File. Let's see. How to open a CPP file. It holds program source code written in the C++. Okay. if you have two, which one should I start first? So if you have the or server first, or P3P, we're changing it up. The client initiates the server. It says the client initiates the client server mall. Here, wait, this might help. The second oh, I don't know about that. I mean, I can look. Try that for the first thing. Second last, sock address? What? What are you guys doing over in programming land? Sock length? What is a sock? Wait, it literally says it's a socket. It tells you the descriptions, you know. Socket specifies the socket file descriptor. Buffer points where the message should be stored. Specifies the length. Socket length is the last one I know. Like, last one you know what it is, or the last one you have. I would assume these are just variables that are about the file that you're... Okay, now one thing I do know is that in Lua, when we're using RedNet in Computercraft, and you're sending files, you have to know certain things about the computer you're sending them to, like the ID. You have to know about the file of the ID of the computer you're sending it to, as well as the one you're sending it from. The socket address has to be the same for both server and client. I'm not sure. You probably have to specify the other ones, though. Let's see. Address have to be the same for server and the client. Socket address for a particular socket on a particular host is unique. So it would be different. They would be different. What's the other one? I don't know. Wait, where did all my stuff go? Oh shit. Here. Yeah, we're chilling. Okay. Okay, so we got 9 in there. We can get the other 9 in there as well. Wait, what? 0? That's not gonna be 0. It's gonna be 10t, so 20 pi. Adding 5 pi every time. 20 pi. 62, yeah, so that's over here. Might be just making random marks on my canvas. Yeah. I only know the sequence 1, server start, 2, client send message, server echo back the message. I feel like that sounds right. Maybe just look into like basic, like what maybe just like P2P startup or like P2P framework. I assume it's something kind of similar to that, but what did I get for the 10 one? Oh, I didn't save it. 5 times, or 5 minus 5 is fine. 10.07. So that's like here, and that's gonna be here. And then we've got 10 pi, 31 here. It's very stretched out in my little diagram here, and then 15 pi plus 15. 6, wait, uh-oh. Plus 5, not 15. 52. I like that. So it goes like this. There we go. I'm gonna get rid of this slug. This slug is scary. I'm sorry. The slug is scary. Okay, so we got that. That's nice. I think we got all those right too. We're winning. What are we doing next? Let's see. Let's see what new friend we're meeting. Oh, Sawblade. Sawblade lady. I am so ready. I'll look at the answer on there. Oh, you have to tokenize an encrypted message? I have a little, I've done tokens, but not like that kind of tokens. I have very, very little experience with anything web related, but I did like more of like a session token. That's what I did. So like I had to basically just talk to an API and get stuff. I mean, that was a lot of work. I didn't have to build networks ever. I've never built a network. I've just used them, and not even that much. Okay, the peripheral speed of a 10-inch diameter. Okay, so we got some things going on here. So peripheral speed. I want to say that's probably v dot is going to be 150 feet per second. When the power of the saw is turned off, the speed of the tooth decreases at a constant rate. So acceleration is constant. And the blade comes to rest in 9 seconds. So from 0 to 9. Our like VI equals 150. Wait, did I just do that? That should be V, I guess. That should be A. I don't know why I did it like that. V and A. And then, yeah, V0 equals 0. Determine the time at which the total acceleration of the tooth. Oh boy, total acceleration of the tooth is 130 feet per second squared. Okay, so we gotta pick a coordinate system. Let's draw our little dude here. So we have a blade. Make it a little bit more bladey. Very important to the problem. We have a constant radius. So if we have a constant radius, the fastest way to do that is probably going to be intrinsic. Because we have that one equation that is the A equals, so A equals the V dot in the normal. Okay, well, let me turn this off. A equals V dot in that normal direction, or in the tangent direction, my bad. And then it's the V squared over rho in the other direction. So essentially what we're gonna do is this tangent direction plus V squared over rho in the normal direction. Background noise, my college work, yahoo! College work buddies. We're winning together. I need to, okay, now that I've like at least gotten my teeth sunk into the problem, now I can draw the saw blade as pretty lady, is the thing. If we can't draw pretty ladies on our dynamics problems, then what are we really doing? It kinda looks like she has a giant eye. She uses one eye. I want to make her like a little funny little lady. Yeah, she's winning. She's winning so hard, TBH. What a little bow. One eyelash. And she has a backpack. I love character design. What journey will she go on? The killing journey. Her head spins like around like this. Just so you can imagine it. She's like constantly spinning. I kind of love her. She's a little creature. I can only draw women in my... No men. Except for Slinch, I guess. Slinch, I think, is a guy. I did see he was my son who has every disease. I really hope I didn't just like directly drink into my mic. That probably was not a good audio experience if I did. So sorry. I'm so sorry, chat. Let me just slurping. What was I gonna do? Things around. I have too many windows up. It's not the right window. Oh god. That's also not the right window. There we go. Kiss kiss. Oh, thank you. Thank you, my awesome mod Chlamydity. Okay, so we know that the We know this component. This bit is gonna be 150 feet per second over rho. Okay, it's in inches, so I guess oh no, times 12 inches per foot. We're just gonna do it in inches because who care? 10 inches equals, which bit? What is this? 150 times 12 divided by 10. 180. It's nice number. We have 180 inches per second squared in the normal acceleration direction, which is great for us. Okay, now we know that oh. Wait, the speed of the tooth decreases at a constant rate. The speed of the tooth decreases at a constant rate, which means there's no acceleration. I lied. Wait. I'm thinking. Chad, I'm thinking. The speed of the tooth decreases. No, there is an acceleration. It's a constant acceleration. Otherwise, the speed would not be changing. Okay, the blade comes to rest in 9 seconds. So we have a constant acceleration, which means we can use the constant acceleration equations, question mark? It's kind of what it sounds like to me. But we don't know what... Oh, we do know what it is. Okay, so we're gonna try and figure out, so... Okay, I don't need to do any fancy equations. We can just use our big brains. Okay, so if it's at 100 feet per second, and it takes 9 seconds for it to stop, then we have the acceleration equals negative 150 divided by 9. Yeah? 16.66666666. 6666666666. Saying 6 too much, doesn't sound like a word anymore. Okay. Nice, we have an acceleration. We love that. So that's fun. What is this? What acceleration did I just find? So that is the tangential. That's the tangential acceleration, because that's just our velocity change. Right, that's our v dot. So what we now have to find is, at the time the total acceleration of the tooth is 130. So we're gonna do a little backwards compatibility. We can change this to be an x. So if we rewrite this, we're gonna have a, our vector, our big vector boy. Right, I want all of them, otherwise I'm gonna get blown up. We have our acceleration that we did, 0.67 feet per second squared. Oh, it's in feet per second squared. We gotta change it to inches per second times 12 inches per foot. They get you with that. Very glad I took data analysis, because I will never be got. Times 12. Oh, this is gonna make it nicer. 200. Actually makes my life great. Okay, inches per second. Squared. Oh shit, wait. We gotta square this. They almost got me. They almost got me again. Oh my god, these guys. They're getting me. 2,400. Is that right? I guess. Huh? Wait, I don't know how I feel about that. Cause wait, that means like in 1 second it's gonna like explode. Wait, no, we're chilling. Okay, they want us to do... Okay, directions are gonna kind of make me insane. One of the things I had on my like, here's stuff I should do in general, was update my signs beam. And now that probably sounds like nothing, but the way that I talk about like skills is usually like beams or frameworks. So if I'm like, I need to get better at doing double integrals. It's like I need to go update my double integrals beam. It might even be this one might be a framework because dynamics and like electrical engineering, so circuits that I'm doing as well, and also mechanics and materials, all have varying, not great ways of doing sign conventions. And when I say not great, I mean they do not have very consistent ways of doing sign conventions that I think are logical. So yeah, for me to use a sign convention, it has to be one, consistent across like the whole subject, and two, logical, because mechanics and materials is very consistent. But for example, they will say, okay, there's a force going down here, there's a force going up here, but always draw your beams in tension. So just draw the force up there, and then you get F equals negative P. And it's like you just messed up the simplest free body diagram it can do. So that's not logical to me. That doesn't pass the logical test. Anyway, but so basically my thought process is, I think it's actually okay. I lied. I think it's okay, but I'm gonna say what I was thinking and why I think it's actually okay. So I was going, okay, well, if we're trying to find the acceleration, we have this negative number here. That's just gonna make like our whole acceleration negative, versus if I was like messing it up and for some reason to be like a positive number, then you know, it's gonna add, and those are actually gonna be different magnitudes, and I would get the wrong answer. Obviously, I can just check if I have the right answer or not, so that kind of falls out. But what I just remembered is we're looking for the magnitude of the total acceleration. The time at which the total acceleration of the tooth is that, which means that the 130 is gonna be our magnitude. So we're just gonna be squaring stuff, which means that our negatives don't even matter. So we're chilling, is essentially what I'm saying. But, okay, wait, this is feet per second squared. We're extra chillin'. We're extra chillin'. Okay. Never mind. Don't listen to me. Or maybe listen to me, but only listen to me like at the very end, because then I'll have it right by then. Okay, so minus 2,400 inches per second squared. And then we have our plus, and our v is going to equal our distance times our time. But, I don't really want to do that. So I'm just going to find the velocity, and then we can figure it out from there. How's that sound, chat? So v squared over rho, which we do know that is 10 inches in the en direction. And I did make it a vector, so let's do this. Because then we're going to make our other equation about the magnitude. So we know it's supposed to be 130 feet per second squared. So 130 times 12 feet per second squared. This shouldn't be squared, I just realized. Because the feet is not squared. The seconds are 200. We're back. We're back, chat. We're so back. We're so bad. Okay. I'm normal. That's gonna be a big number. It's gonna be a big number. What is that? 130 plus 12? 142? Not plus 12. What am I doing? Times 12? 156. Nope, that's not it. 15,600. That's not a great way of saying that. 1,560. They're all bad. They're all bad. Okay. So that's going to be the square root of 200 squared plus v squared over 10 squared. So I just took the magnitude. Unfortunately, we are going to have to multiply this again. I feel like I've definitely missed a sign somewhere. Did I divide this by 10? Wait, what did I do over here? No, I did. Divided by 10 inches. Did I do this right? Wait. 150 times 12 divided by 10. I guess that is right. That's just so weird. Because like 150, well, I guess it's 15 compared to 16, so that does make sense. Wait, but then wouldn't it slow down in like 1 second? No, wait. I'm thinking. I'm cooking. Give me a second. Hear me out. I feel like this is too big. Okay, maybe I can't just divide it by 9. Can I divide it by 9? Yeah, I can, because that's going to give me the right units, if we think about units. What, 16 times 12? Yeah, that seems about right in terms of, like, calculator things. I don't know, this is just going to be a really big number, I'm kind of worried. But it's okay, maybe that 200 squared is going to carry us a little bit. But this one's just about to get squared. Okay, well, whatever. Let's see how this comes out. I shouldn't be so doomer. Oh, maybe I should be a little more doomer. 2,433,600 equals. So, sorry, minus 200 squared. 393,600. Still absolutely massive. Okay, we are taking the square root, which is v squared over 10. Okay, wait, maybe we're getting closer. We're taking the square root, which is v squared over 10. I like that we're taking the square root. We're getting to that area. Uh-oh. So, 1547 times 10 and squared. Or not squared, square root. I don't like the times 10. This 124 inches, inches, inches. Inches per second. Okay, wait a second. Okay. Let me cook. Oh shit! Wait, our initial velocity is not... Wait, Wait. Our initial velocity is way higher. I was looking over here. Oh, it's 150 times 12. Oh, chat, we might be winning. We might be winning, chat. I was looking over here, I was like, oh my god, it's like so short. We're gonna get rid of all the velocity we have so quickly. Oh, wait a second, chat, we might be cooking here. Okay, so the way we do this is by saying, if we want to try and find the time, we just say like a equals vt. No. We think? Yes. No. Yes? No. What? Maybe. There's a version of this. X equals vt. V equals at. That's the one. Okay, so v 124.38 inches per second equals... What was our acceleration? 130 feet per second. So 130. Gotta grab dinner because I finished work. Have a good dinner. It's 12 times t. I'm worried, chat. I'm worried. I'm not gonna lie. 124. Uh-oh. This is like not gonna go well. Yeah, that's not right. Okay. I just tried to print that. Let's not print this. Okay, so there's something wrong, but I think we're close. I think we're close. I think we're really close. Wait, so the acceleration at that point... I don't know if I can just do that easily is the thing. I want to say you can, though, because it's constant acceleration. Maybe I'm like doing it the wrong way. If it was a equals vt, does that make any sense? No, it doesn't. But I actually don't know if this... The constant acceleration... No, that doesn't make any sense. Wait, I have to use delta V, don't I? Wait, I just put this on my dynamics equation sheet. V minus VO, V minus VO, V minus VO. Wait, does that make it worse or better? Wait, V minus VO. Our acceleration is gonna be negative. Wait, we might be cooking, I got too excited. Minus our big honking number. Inches per second equals, this is all over the place. Let me like put this under here. Equals V. Let me like write some stuff down. Me when I'm not writing anything down. Okay. Equals A, which is the 130 feet per second, times 12 inches per second. T. Okay. So 18 whatever minus the 24 thing divided by 130 divided by 12. Oh shit, we're still off. Like kind of a lot. Okay, maybe I feel like the logic is right though. I feel like we're right in the sweet spot in Logic Town there. Like everything kind of makes sense, but it also just doesn't really vibe, does it? So we have a constant acceleration, and it comes to rest in 9 seconds, and it starts at 150. What if I just did it in feet? It shouldn't matter if I do it in feet, but like, what if I did it in feet and it like worked out nicely or something? Let's see. 150. Maybe it's some calculator stuff. 150 times 12 is 1800. And that's gonna be, we use that later. So V times T equals A. Wait. Okay, V times T equals A. Delta V equals AT. Oh no, so it'd be V over T equals A. Yeah, so 150 divided by 9 seconds is 16 feet per second, and then we times that by 12, and that's 200. So we have our correct, and that's just talking about the velocity change, so that's gonna be our tangent, so that's good. Then our other one is gonna be V squared. So, oh, wait a second, did I never square it? Oh shit, I never squared it. 150 times 12 squared. Oh my god, that's so much bigger. Oh, wait. This is it. This is definitely it. I mean, my thing is all over the place, so I definitely need to like move some stuff around, so this stuff's gonna go down. We're gonna do this. And I'll write some headings on it and stuff, so I can kind of explain what I'm doing. So this was find A. And then we have find, I stole some of the paper there. Okay, this is like find the like AN, I guess. And then solve for T, or solve for V at A equals 130 feet per second. Okay, so if we square this, we're gonna get a much bigger number, which is what we should have done, times 12 divided by 10, is in the millions now. 3,888,000. much better. So then when we plug this in, we're gonna get this minus a 3 million, which is gonna give us a different velocity. Wait, is that true? Oh yeah, because this is not 200. This is 3 million now. Wait, no, the 200 stays. I lied. Wait, no, this all stays. This all stays. This is right. This is right. We change this. This is 3 million now. Wait, oh, okay. No, we're okay. We're okay. I think this feels like a lot. Now I feel like I've gone the other direction, and now it's like, okay, we've got 3 million. 3 million minus 124 or whatever. Where's that number? Do I have that number? I do. It's that, and then this divided by 130 divided by 12. Okay, now we've gone in the other direction where this is too much time. That is 2,000 seconds. Okay, we have to go back to the drawing board. I don't know where I went wrong, but we'll go through it again. So this part is right. This part I feel like needs more checking. So what I did was I multiplied it 150 times 12, and then I did it. But let's try and see if I can get the same number. If we do 150 divided by 10 divided by 12. No, sorry, 150 squared, and then divided by 10 divided by 12. Okay, I don't know why I thought that was going to give me the same number. It's not going to give me the same number. I think I might need to do 150 squared times 12 squared would be the same thing, right? Yeah. Wait. I just did this again and it gave me a completely different answer. What? Wait, what? Oh, because I multiplied it by 12 again after. Oopsies, I didn't mean to do that. Okay, this is a more reasonable number. We've gone down 3 sig figs, which actually is pretty good because... Wait, no, we haven't gone... We've gone down 1 sig fig. Okay, chat. This might not be... It's not Jover, but, not yet. Not yet. This is all right. I mean, I can check it again, but... Okay. 3, 2, 4... 000. So 324,000 minus the 124. This music is exactly how I feel. Okay, divided by 130, divided by 12. Oh, we're still 2 sig figs off, and we're also not in the right magnitude. Ugh, that's rough. Okay, let's check the velocity calculation. So we definitely have the 200. That one is not negotiable. The 150 is what we're getting by doing 300 times 12. Okay, let's write this a little, 130, not 300. So 130 inches, or feet per second squared times 12 inches per foot is what we're getting there. And let's just check that math. 130 times 12. Yep, okay. So then we square that, this squared, and that gives us this big number. And then we're gonna subtract 200 squared. So that's a slightly less big number. Square root of that. We multiply it by 10, and we take the square root of that. It's 124 inches, okay. That would be like 10 feet. Let's just see. If it was 10 feet per second squared, let's see, like 10 feet, we would square that and we would divide it by 10, so it would be like kind of like 10 again. And then we add our sort of constant one, which is like 16. That would be 130? Wait, what? That feels weird, actually. Oh, wait, no, that shouldn't... What? This feels odd. This feels odd, actually. Should I just do it in feet? Should I just... They probably want to do it in feet. They probably want to do it in feet, but the thing is I don't want to do it in feet. I want to do it in the smaller unit. But I guess feet would make more sense, because then I don't have to convert, like, half of the units that I'm using. Fine. We'll do that. Let's see. Maybe we can find the math error when we do it like this. So divided by 10 inches divided by 12. Right, so 1 foot times, right, like 12 inches per 1 foot. Okay. In feet. So that's going to give us 15 times 12. 180. Which, just for reference, is not the same thing as that, but I think if we were doing 180, then that times 12. Also not correct. Wait, that's weird. I didn't square it. Put the squared on there, Damien. Okay, 150 squared. Squared. Divided by 10 divided by 12. That times 12 is the same thing. Okay, so 27,000. Whistling. You can't hear. Okay, so we got a kind of nasty number here, but that's okay. That is our change in speed. And then we're solving for this. So the 10 inches is fine, but I'll just, you know, divide it by 1 foot divided by 12. Kind of scuffed, but that's okay. So in this case, we would just have 130, and I can get rid of this. Feet per second squared. This is not 200 anymore, this is 16.67. Still gonna be a big number, but not as big. So 130 squared. And then we've cleared out the square root, so we're just gonna subtract 16.67 squared. So 16,621. I don't need that. Feet per second squared. Would it still be feet per second squared? I'm not sure what the units would be on this one. I'm just gonna do 12 up there. 12. Divided by 12. Okay, so we got this number. Oh wait, that's weird. I'm gonna get rid of this. We'll just say what v equals directly. I'm hoping this works out, because if it doesn't, then I gotta go back to square one, and that would not be entirely fun, but you know, we'd get through it. 10 divided by 12, and let me take the square root of this. 117. That is weird. I got cream cheese bagel and everything bagel too? That sounds awesome. That sounds great. I don't know what I'm doing for dinner tonight. No clue, actually. Now we can see that I got very different answers. Because if you look at what I got in feet per second, inches per second, I got a larger number than in feet per second, but only by like, not by magnitude 10, so I definitely did something off. It's so young. That's awesome. I'm so glad for you. Wait, what was that I just erased? V. Oh, minus initial velocity. What's our initial velocity? I forgot. It's like 150? Yeah. This seems like we might be winning. Perchance. Where's my other accelerator? Negative 16. I'm just hoping for the big happy moment where it like all works out, you know? Praying. It does not look like we're getting there, gamers. Yeah, we are not there. I got like 2, and it should be 8. So that's unfortunate. I love it when a problem beats me. I love it when it wins. Me when I don't solve the problem, I get solved. Okay, this is a classic case of skip it and come back to it. Damn, I know, right? It would have been so nice. I got smited. I was taking a screenshot of the next problem, so I just saw the smites just like freeze in midair, and I was like, oh damn. Mega smited. Oh my god, a motorist. She's slaying. She's slaying. She's slaying. She's slaying. This is maybe the first time I've seen the pronoun her used in my entire study of engineering. She's literally slaying. Motorist. A motorist. I don't know who she is, but she's a motorist. Let me turn on a light so I'm not just cowering in the darkness. Back. Oh, man, noise. Worst noise of the year, sorry. I would love to have a worst noise of the year. It's only January, and I've already made a lot of bad noises. A motorist starts from rest at point A, when t equals 0, increases her speed at a constant rate, and enters the highway on point B. Knowing that her speed continues to increase at the same rate, this is just like flowing over my brain. Okay. So v0 equals 0. A equals const. So I think we can kind of split it into 2 problems. One like circular motion, and then one you know. One flatline kinematics problem. So that's how I'm thinking we do path. We start with path. Knowing that her speed continues to increase at the same rate until it reaches 100 kilometers per hour. So VF, we have like a V, I guess I, and a VF. We don't know what that is. Or VB, I guess I should say. VC equals 100 kilometers per hour. Maybe the units will be nicer to us this time. Determine the speed at point B and the magnitude of the total acceleration. Okay. These are our useful little guys over here. I'm also I don't even need to draw it, but the motorist is Peach. She is winning. She's on her, this is for Mario Kart. We all know. I don't know. I don't know how Peach's hair goes. How does Peach's hair go? You know, I could draw Peach's hair anyway and just be like, oh my gosh, this is a new Peach design. What if she had short hair? Everybody like, yeah, so real. Her eyes have like one of these going on. No lashes. She's winning. I hope she's winning Mario Kart, actually. Make her chonkier. There we go. She has the earrings. She has those swag earrings. I think she has a necklace. Does she have a necklace? I don't remember anything. I feel like this is also anime Marge Simpson. Think of one of those anime artists who like has only ever drawn one woman ever, like trying to draw Marge Simpson. It's just, she's just Peach. This is so cute. Got like little, okay, I'll just draw these ones, little hair twirlies. This is not Peach's hair. I don't know anything about Peach. I I have to draw like something from the problem, otherwise I get sad. Like, hey, if you're gonna make me do applied math, she's applied, okay? Don't worry about it. What does that mean? I don't know. Okay. So V equals, we don't know. Oh, okay, we know rho. We actually don't know what V is. And we kind of know what A is going to be consistent. So I guess let's do like the straight line. Straight line. So VC minus VB, where we start at, equals the same acceleration we have times T. Oh boy, we have nothing. Or, okay, wait, we know this. 100 kilometers an hour. Okay, the time might not be the play. It's actually not the play, I lied, because we have a distance. So let's do V squared minus VO squared equals 2AS. Straight line. So V squared, 100 kilometers per hour squared minus VB squared equals A, which we're going to be able to solve for in system equations, times 100 meters. Oh boy. But we're getting there. That's something. What else do we know? We know that A equals okay, we know some things. We know, we'll go for the curve now, because that's the only equation we can write for the straight line for sure is these. There might be another one, but whatever. I need to start bringing time in there. I don't know how I'm gonna do that. Okay, we know that A equals the change in velocity in the tangent direction plus E squared over rho in the normal direction. We don't know A, and we also don't know delta V. We know that it's a constant, but we don't know what it is. Right now we got 2 unknowns over here and 3 unknowns over here, so we're gonna need one more equation of some kind. We could relate some stuff with time, probably, because we know that A. Actually, so the V squared over P is due to the turning part. So when we turn, we're getting V squared over P, and we're adding that sort of onto our other acceleration. But our normal component is only this V dot. So really when we say this, we're only saying this. This is this. I really shouldn't say A, this should be V dot. So now, and we can... It doesn't go red. It doesn't go red anymore. Oh no, now I have to look for... Wait, okay, is it still like just as loud? Oh shit. I jinxed it. I literally was like, I hope nothing evil happens this stream. I hope no mic demons come out. Earlier. Oh, I thought I kind of fixed it. I wonder what it could be. I mean, my phone? Is it my phone? Let me see. This is evil. Yes, it's just, no! That's so evil. It's actually so evil. It was yaoi and I'm not wearing headphones. Ah. This is so sad. We'll figure it out every single time, just like we figure out this dynamics problem. Bring it back. Oh my god. Someone's like dropping rocks on me upstairs. We have V, or delta V equals, I guess we could say a delta V. I had to ascend Cookie Clicker, now everything feels so slow. Oh, I wish I could play Cookie Clicker. I could, I think. I don't know where my save is. I think I have a save on... Maybe I don't have a save on this computer, actually. You can also say that delta V equals V dot times T, which... we know that delta V is, like... VB... or V... or 100 kilometers... Just writing down every single equation that we have, in hopes that if I smash them together enough, then we can get the equation we need. Get rocked. It's like when you guys drop emojis on me. We got this one. Now we have another equation. I restarted my Cookie Clicker after so long of not playing and it feels so beautiful. Maybe I'll just start a new save. Maybe that'll be this weekend. Or some other time. I'm like got a month in. I want to do like it would be funny to try and do like an optimal Cookie Clicker run. I mean, I'm sure people have done it, but like me doing it, I feel like it would be really bad. Which is why it would be funny. This is kind of like a rock. Is that the Earth? Oh no, the Earths. Fuck, okay, wait, so we don't know like anything. We're so unknowledgeable. I'm up to 4 unknowns. I need at least one more equation. But like I also don't know A. So let's wait. How many unknowns do I have? Okay, so this I know. No, I don't. I don't know what this is either. That's an issue. If I knew what this is, then I would be fine. No, I wouldn't be fine. I mean, I guess I could find... Ooh. Ahwa. Ooh. Okay, if I was, like, at here, there's not gonna be any normal acceleration. Because I'm just gonna be tangent. If I'm at here, then all of the acceleration is just there. That's not useful. What am I... What's happening? What's happening? Okay, I don't know any times. I know that she just starts at 1 speed, and then she goes around a turn, and then she goes... This sounds, like, insane. This sound... Okay, are the answers to this problem, like... Oh no, they're real answers. Okay, I'm just gonna be like a... You can't solve this problem. Okay, okay. I don't know anything about her speed, except for the fact that it's the same at B as it is at B. It's the same at the end of the first part, the beginning of the second part. Increases the speed of her automobile at a constant rate. So V dot is constant, but we don't know it. Her speed can increase at the same rate. Okay, what else do we have? Let's just like look. Let's look with our eyes. We have delta S equals VO2. Ooh. We might be able to use this because we can do a delta S, and we can. This is insane. This is like every single equation. I'm just throwing them all in there. I don't even know if this can give me anything. Fine, I'll try it. I don't have anything else. I don't have anything else I can do. We know a delta S for the curve, so delta S equals, what would that be? VOT, this is 0, plus 1/2 AT squared. This A is going to be V dot. delta S equals 150, so it's 2 pi r, so 150 pi over 2 plus 1/2 v t squared. I can't even, like, okay. What? Okay, wait, vt squared, vt times t, we can put that in that other one. This is, like, awful. This is so hard. Wait. My brain just started working for a second. If I solve for v dot in this, I can do that. So v dot, what if I just put this on the fucking matrix? Didn't have to do any work. Okay, sorry, I'm a hater. Well, it's 100 meters. Oh my god, it's meters, kilometers too. God damn it, 100 meters is like 0.1 kilometers. Let's put in that. Okay, so let's just do out the math. So 100 squared is 1,000, divided by 0.1 is 100,000. So 100,000 kilometers per hour minus 10 VB squared. We got that. That's good. I like that. It's kind of, not really, actually. Oh wait, if I take the derivative of this, I can get acceleration in terms of VB dot, or VB. Is that useful? I don't know if that's useful. Is it useful? I feel like it's not useful. Wait, perchance? No, I feel like it's not that useful. I think she said at one point, you have to. This is like hurting my brain. This has been so nice just in the background. Thank you so much, popular streamer and V-tutor Damie. me losing my mind over this dynamics problem. How does it go? Thank you so much. I'm glad you're enjoying it. I mean, I can make a 5th equation. Hear me out. 5 equations. A. But what does A even mean in this case? A is like V double dot. I don't even have V double dot anywhere. That's like the magnitude of this. Get spun? I actually probably have to end soon because I have to go pick up the lion. Let me text one person. We have too many lions. We have 2 lions in our house right now. If we don't make another equation. Okay, but Clem, what if I made another equation? No. Fundamentally, something is wrong. Something is wrong. Oh, so many lions, no more equations. I know, I have too many everything. We have 2 lions in our house. We had 2 lions, 2 symbols, 2 sets of symbols. 2 drumsticks, for some reason. Not a drum. We're not fancy enough to get to keep the drum. Our drum, by the way, like, if you haven't seen, or, you know, depending on lion dance, our drum is like this big. If I'm standing at it, where does it come up to on my body? I miss sexy. I also miss sexy A block because I could do that problem. Wait, but you didn't see the cute motorist. She's winning. Her. She's just Peach. She has a cool racing jacket on though. She has proper safety. She has a motorcycle helmet that is off screen, not pictured. She's awesome. I wish she could just tell me her speed, you know? You know what I'm saying? Aw, so silly. She's so silly. She's so silly. She's so devious. I'm not gonna tell you my speed. You silly cat boy. It's a little bit better. A little bit more realistic. I can only draw women on this stream, just to, you know, make up for that one guy who was like, "There's no woman in engineering. It's not possible." I'm like, what? What is this? I forgot I was drawing. That's how big. That's not how big our drum is. This is a lie. It's like maybe this big. That's closer. It's a big drum though. We don't have that in our house. We do not have space. She's so silly. Okay. How do I do this? I'm molding so hard. But what if I like did okay, I don't want to do polar coordinates though. Don't bring him up, I forgot. I know, it's a blissful world. Right. I feel like it's a center, it's a radius that doesn't change, and in this world we use path coordinates when we have an instantaneous sort of radius thing, or it's a circular motion thing. So why, where do I go? Where do I go? Chat, I'm so lost. I was like, this is gonna be easy. Look, we have 2 unknowns. Just make another equation. Oh no, then we go down to A and we have 1, 2, 3 unknowns. And so that doesn't solve any of our unknowns. Now we need another equation. Now we make this the second equation, and this gives us another unknown, and then there's another unknown. Well, we do have 4 equations for unknowns that are distinct. So if I were to put them all into a thing, then it would be great. I don't really know how to do that. Is the issue. I feel like if I took the derivative of something, I don't know. This is here. I move that there. Okay, that we're winning. That won me the game right there. I'm coping so hard. Okay, where do I go? I know, like, in my mind there has to be something about the velocity, the centripetal acceleration. The v squared over rho has to be like nicer to me. Do you know what I mean? But right now we have no other a's, so I can't like plug an a in anywhere. You know what that means? Second derivative, baby! This is great. This is just gonna be minus 20 VB. Doesn't solve any of my problems at all. But if I changed this, we could say A magnitude equals v dot squared plus wait, v dot. Wait, that's an acceleration. Oh no, chat. Oh no, what's v dot? Wait, we have some v dot expressions. Do we have any v expressions? Why do I have so many v dots and no v's? Oh wait, vb. Wait, is it vb? Can I use vb? If I know the, oh well, yeah, I can use VB. Oh, okay, wait, we're cooking? No, we're not cooking. Don't let me say I'm cooking on this stream. This one is not, I'm not cooking at all, chat. I'm cooking bricks. Okay. Here's another equation that we have. Equals 20 VB. Fifth equation. Fifth equation. Okay, so I have no clue where to go from here. This is like a tangled mess. I am the tangle. I've become what I sought to destroy. So yeah, that's a little sad. Like, I don't know. The one we did in class was so much easier than this. Because it wasn't like, hey, here's only, oh, you want to know one variable? 2 variables. And you have the knowledge that A is a constant, and you need to find 5 variables. Like, what? I might be overcomplicating the problem. Me when the two problems that I can do, I just don't know where to go on either one of them. This one is like scuffed though. This one I feel like I'm very close to. If I can get this one, this is one of those things where it's like, I think I need to go away and come back to it, but let me try to push just a little bit further on it. Let me also take a look at what the next one would be. Oh, see, this is what we did in class. Look at this. This is great. I mean, it's not great. It kind of is a little bit, pointy, if you will. We got a guy like this, so the pin B is free to slide along the circular rod, so we can, like, the circular slot and along the rotating rod. So assuming that the rod OC, which is the one that's straight, rotates at a constant rate, theta dot, so we use polar, so that the acceleration of pin B is of constant magnitude, and determine the direction of the acceleration of pin B. Okay. This one is a little bit insane as well, but okay. It rotates at a constant rate, right? So it's a angular velocity, omega. Well, probably my least favorite thing to draw. Also, winning the prize. There are a lot of good things to draw in math. Like, you got phi. Phi is great to draw. It's like a little hand. Like, oh, I'm gonna like grab this. Oh, I'm gonna grab it with my little hand. Hee hee, I'm evil. An evil hand. You got like theta's great. Theta's just like a really happy guy with his eyes closed. Alpha, so fun. Like a goldfish, like when you were a kid, when goldfish was a single line and also an alpha. Actually, there's some worse ones. Lowercase gamma, which I forgot how to do. It's like this, or something. That one's bad. Lowercase gamma is bad. I don't remember how to draw lowercase gamma, actually. I had to learn how to draw it for 2 seconds. Draw an aquarium with math symbols. Just like asymptote. He's down there. He's with math symbols. So definitely there's like a big alpha. And there's like a really thin gamma fish. Like these guys. Then you have some plants. Getting a little lazy. Theta I. You just have letter E. My beautiful aquarium. I was trying to think of what could be an octopus. Oh, omega, I guess, maybe? Like an octopus, sort of? They don't have much enrichment. You're right. E for enrichment. That's their vitamins. You know, just a couple E's around, just some classic decor. Imagine if I turned in my homework with this. What? My teacher's gonna be like, "You are dumb." And then I would say, "Professor," and I would make this face. That kind of face. I would say, "What about whimsy?" Please do. Holy shit, look at the asymptote on that mother function. I cannot turn this in. This one is... Okay, it tells you a lot about me, but like, I feel like I can turn this one in. But I can't turn this one in. What about whimsy? But I would say it like this, like, what about, you know what I mean? What about, like if I was like speaking in cursive. Whimsy. That's how I would say it. I said a swear? A holy shift? Oh. Sorry, I say a swears. What about whimsy? I need an emote toggle for my model. It's a smug face. I could do that. Emote toggles on models are like so much more annoying to do because I have to rig my face. I have to put it on my face is the thing. I can just like, I can just have an image that shows up over my face. That would be easier. This one is, oh wait, I didn't even do anything for this one. I just drew an omega. Sorry, I needed to get rid of this. It's still there. I swear when I'm like, I need a this toggle. Well, when I do my left hand model, maybe I'll make it like really emotive. Okay, I'm gonna work on this for like 10 more minutes and then I have to go. Certainly. Maybe 5 more minutes. Okay, I have 5 more minutes and then I have to go. Okay, that's my hard limit is 5 minutes. Okay, how much can we speedrun? So we got that. Acceleration. Okay, so A for, this is all we know. That's all they tell us. Essentially. So A equals, not that. A equals, okay. R double dot. R double dot minus R theta squared ER. Oh, wait. Oh, it's okay. I was just gonna say that there's gonna be some parts of this that are 0, but that's okay. It's a great song to end on. Okay. So if theta dot is saying the rod rotates at a constant rate, so there's going to be a part of this acceleration that is not existent. So this is not existent. So we only have r double dot minus r theta squared ER. And this is 0. Because theta dot is 0. No, I lied. It's not 0. What am I talking about? This is constant. So now we just have to show that r double dot is constant. R double dot equals what? It's the rate of the rate. Do I have like a relation between r dot maybe not. I say, do I have a relationship between like r double dot and theta double dot? Because theta double dot is 0. Theta double dot equals 0. No. E theta XL. Right? Yeah? Me coming in like, I'm gonna conquer this. Me be like, why do I have 5 equations and 3 unknowns? Okay. This is a weird way of show the acceleration of pin B is it a oh, I see why they're doing that. They gave us the radius of the I was like, what is this here? This is weird. But yeah, so we don't have any theta acceleration, I think. Or do we? No, because I mean, well, this would exist, wouldn't it? This sad music in the background. I'm sitting at a single desk with a flickering candle and a feather pen. Got ink all over my hands. Going insane. Oh, I didn't even have my drawing tablet up this entire time. I've just been psychically beaming. Well, that's why. That's why I couldn't do it. I didn't have my drawing tablet, guys. Don't worry about it. I'm gonna have to think about this. Okay. Is there no E theta? So E theta is a mindset. No, E theta is not a mindset. E theta, it has the double dot, which is 0, but it's gonna have a constant rate for the other one, I think. I think we need to figure out what R theta is. I need to draw Damie with the feather and ink. What is r theta? What is r dot? I might actually have this in my notes. Wait, I think r dot equals like r theta dot or something weird. What does r dot equal? Can I get a proof? Can I please get a proof? Is there no relation between these? It's actually not been Damie doing the problems. It's been someone else, and only now am I taking over. Yeah, the bad guy has been doing the problems. Oh, you know. Who is it? Oh, you know. The guy who's bad at Don't worry about it. Hey, we did this one. That's a win. We made a valiant effort on 3 of them, which is, you know, well, this one is a very valiant effort. This one is... I don't know what that is. I don't know what's up with this one. Maybe it's the peripheral speed is sort of an incorrect word. What is peripheral speed? I want to say it's tangential speed. Peripheral speed. Huh? Huh? I'll be the Damie fan artist. Oh my god, I would cry. That would be so beautiful. What is peripheral speed? I think it's just the outside speed. This is like grinding. What is this? Yeah, this is odd. Calculations. Okay, the speed at which the drill is moving, it is RPA, yeah, RPM. So it just means the tangential speed. I don't know why it's being a hater. Maybe it's just my if it's my calculator, I'm gonna cry. Okay, I need to go. It's time for me to go. Time for me to go. Eat something before my practice starts. I will probably be live this weekend at some point. I don't know when exactly, but yeah, I might be working on this still, but I'm probably gonna try and crank it out tomorrow if I can. Okay, everybody. Have a nice night. Have a nice day. Hope you guys have an awesome time. All right, I will see you all later. Bye. Bye.